Okay, I'm going to assume you all understand the problem and have watched Kwong's editorial because I'm going to be jumping straight into the online solution. So we have an array of events and several queries on some ranges of this array. For each query we have a money total that is initially $M, and we then iterate over the array over the query range, updating the money total by the value we are currently iterating over. If the total was to become less than 0, we must borrow money to make it equal 0, and what we're asked to find is the number of times we must borrow and how much money we will have left over after all the events in the query range. Kwong explained an offline solution using union find, and I'll be going over an online solution using segment trees, since that's what we're currently learning in April camp, I guess. Offline means you're basically given all the queries at the start and you can process them all at once, whereas online means you're given the queries one by one and you're expected to answer each query before you get access to the other queries. On DMOPC, you're not actually required to have an online solution, but what I'll be going over today is an online solution. So I can process each query one by one. What we're trying to do is come up with a segment tree that can answer the number of times we must borrow money and the amount of money left after each query. And I'm going to be handling these operations separately, and I'll start with the easier one, which is determining the amount of money left after each query. And for this query, there's two cases that can occur, really. The first is you never have to borrow money. So suppose this is you're starting at $M and you have $0 here, and you have several events which never cause your total money to drop below 0. In which case, the money left over will be $M plus the difference from the prefix sum from, let's call this L and this R, where this is the total money when you're iterating over event L, and this is the total money when you're iterating over event R. And if total money never drops below 0, then it's simply M plus the difference between the prefix sum up to L and the prefix sum up to R. Right? Yes, this is being recorded. So that's the first case, and in the second case, we actually have to borrow money. So I'll just draw. So if we have to borrow money, there will be some point where we last borrowed money, and from this point, the difference between the prefix sum of this point and R is what the answer to our query will be, right? So you can't simulate it in ON time, and the reason for this is there's 300,000 queries. So that would be ONQ, which is very slow. So Kwong's solution yesterday was offline and ran in ON plus Q log N or something. And the one I'll be going over today is online and has a worst case of N log squared N and a best case of N log N log log N, which I'll explain how we get that later. Okay, so in the case that we have to borrow money, how can we distinguish between like the two cases? So how do we know when we have to borrow money? Well, if we look at the graph of prefix sums from L to R, it's pretty clear that we'll have to borrow money if and only if there is some prefix sum or some point such that the prefix sum to that point subtract the prefix sum to L is greater than negative M, because then you'll have lost more than M dollars, so you obviously are in debt. So by checking this condition, we can determine which of these two cases we're in. And the first case, it's fairly easy. It's just M plus the difference between the prefix sum at L and the prefix sum at R, right? Because you're never changing the prefix sums because you never have to borrow money. And obviously the increase is just this. And in the second case, it's slightly trickier. So we need to find this point, this last point where we borrow money, if we want to determine how much money we have left over. So I'll make a more interesting case, because all of these we never have to borrow money more than once. So I'll just continue on here. So this is just going to be a graph of the prefix sums, and I'm just going to ignore borrowing money for now. For now, I'm just going to simulate this, and after we can see if we can make any observations. We start off, first event, we lose some money, but we don't have to borrow anything, gain some money, lose some money, gain some money, lose some money. Okay, now we are in debt, so we take this point and set it at 0. This is now the new 0, right? And you could think of it as this entire suffix has been shifted up. And what we notice is in this suffix, the relative order, if you sorted the prefix sums, the relative order does not change in this suffix because you shift the whole thing by a constant. And so therefore, if there was some prefix sum smaller than, I'm just going to call this the debt point, where we're first in debt, then obviously we'll be in debt again once we reach this lower prefix sum. And we can continue this logic until we reach the point of the lowest prefix sum. And the lowest prefix sum is the last time you'll have to borrow money. So we can find the lowest prefix sum with a range query. What do you mean if you sorted the prefix sums? Okay, so basically the smallest point on this graph, or in this suffix, remains the smallest point when I shift this suffix up. Yeah, so if there was some prefix sum, so the smallest point as in just the lowest point, if I took all the events and I didn't bother about borrowing money, when do I have the least amount of money? Yeah, like the lowest. So the last time I'll have to borrow money is at the lowest point on this graph, basically. If that lowest point is less than 0, because otherwise you fall into this other case. Yeah, so we're trying to construct a segment tree which takes an array of prefix sums and finds the smallest one. Do you all know how to do that? Because I'll just skip on to... Yeah, okay. So, in the first case, where the smallest point, or the lowest point, is not less than 0, we simply take the difference between the prefix sum at L and the prefix sum at R and add that onto M. And in the second case, we have to borrow some money, and the last time we borrow money will be at the lowest point on the graph again, or the lowest prefix sum. The amount of money we're left over is the difference between this lowest point and however far it gets up at R. So the difference between the prefix sum at the lowest point with the prefix sum at R. And you can answer this with a range query. So that's the first query, first half of the query done. And does that all make sense? Yeah, this is just a query to find out how much money you have left at the end. So you're all comfortable with that? Because I'll move on to working out how many times you need to borrow money now. Okay, so if we go back to our observation that every time we borrow money, if there is some point to the right of that point which is lower, we'll obviously have to borrow money again. And we can rephrase this as, for each point, if all the points before it, all the prefix sums before it, are greater, then we'll have to borrow money. If the prefix sum is less than 0, of course, or less than negative m. You know what I mean. So, if for each query we could construct a sorted stack-like array where we maintain all these points which are greater or less than all the points before it, and I'll call this sorted array structure a minimum change array, because if I was to iterate over all these prefix sums, every time the minimum changes, if I was to maintain the minimum, then I would have to borrow money. So yeah, if I was to calculate the minimum for an array, how would I do it? I would iterate over the elements, storing a minimum, and if the element I'm looking at is less than that current minimum, then that's the new minimum. And every time I change that minimum, I would add it to my minimum change array. And do you see why every element in that minimum change array you'll have to borrow money? So yeah, if we could calculate for each query this minimum change array, then we could answer this query, right? Because all we need to find is all those minimum change points which are less than this threshold, which is where you don't have to borrow money. But unfortunately, there's no efficient way to construct this minimum change array, or at least that I know of, for each query. And if there was, it would probably be offline anyway, so that's not what we want. So rather than trying to construct this array for each query, why don't we try and break our prefix array into chunks and then construct this minimum change array for each chunk, and then see if there's some way where we can combine them. So suppose we had pre-computed the minimum change array for two adjacent chunks, and now we have a query which covers both chunks exactly. Essentially, we want to merge these two minimum change arrays. Now, these are going to be maximum change arrays, just because they're easier to draw, but it's the same thing. So I've got one chunk here, and second chunk here, where I've pre-computed the minimum or the maximum change arrays in this case. And now I have a query that covers both ranges. So what I really want is to merge these two. But obviously merging them would take O of the size of these arrays, which is not fast enough. And instead of actually merging them, we can perform a binary search on the right chunk for the height of the rightmost element in the left chunk, and then we can just pretend that these have been erased. Now we can just binary search each of these remaining elements. So for each chunk, we look at the remaining elements and we binary search for the elements that are greater than or less than the threshold for having to borrow money. What's the prefix array? So you've got an array of events, and rather than looking at the events, you just look at the total amount of money you have at that time. So yeah, we can just cross these elements out and then binary search for the minimum threshold, and now we've taken two separate chunks and we've combined them in a way. It takes log n to binary search each chunk. So now how can we chunk our prefix array efficiently? So how can we get the optimal use of this ability to combine our minimum change arrays? You could chunk your array into sizes of square root and basically just square root decomp, and that will get you square root chunks, and you have to perform log n for each chunk. So for each query you would get a total complexity of square root log n, which may even pass, but it's not the best. If you've got a square root, you can probably turn it into a log, and that's exactly what we're going to do using a range query, a segment tree. I mean, so in a segment tree, when you query, you get log n ranges. If we've got log n ranges and we have to do log n work for each range, that means we only have to do log squared n work for each query. Okay, so to recap, we have a segment tree, and in each node we store the minimum prefix sum and this minimum change array for the corresponding range. It's basically just build a minimum range tree. Yeah. So the tricky part is how can we efficiently find these minimum change arrays, and it's actually just do it basically, and I'll explain why that works. I'm kind of confused as to why we can just yeet the small values away when merging two sorted stacks. So we're having a query on, let's see if I can go back. So suppose we have this query here. Let's construct the two sorted stacks, but I'm going to invert them. So this sorted stack corresponds to this range of this query range. And let's make another range here. And these have actually got to be a bit bigger because... So basically you've got these two sorted stacks from these ranges. These two ranges produce these sorted stacks. And this point in the right range is not less than this point in the left range. So we won't have to borrow from this right range, from this point here, right? If I only look at this right range, it is a minimum, but if I look at both ranges, it is no longer a minimum. So I can just take this away. And rather than actually doing that, I can just binary search and just pretend. Yeah, so these are minimum change arrays. So basically, if I were to iterate over the prefix array, maintaining the minimum, every time that minimum changes, I have to borrow money. So like I would have to borrow money here, because it's smaller than any of these. Well, except if it's greater than this threshold where you don't have to borrow money. It's like you would have to borrow money here, here, and here. And then so if I were to do this in my segment tree, where I've got two ranges that cover this query range, I would first binary search in the right, and I'll remove all elements that are greater than, or in this case less than, this rightmost element, because that is not smaller, and I won't have to borrow from there. So I'll just remove it. And now I've got, well, I won't remove it, because I won't physically delete it, because I may have to use it in a future query, so I'll just pretend it's gone. And now I need to make sure that these elements are below the threshold, so I'll range query again, and I find out that these two are below the threshold, so I'm left with these three, which are the points where I have to borrow money. How do you know if they're below the threshold? So I would have had to have accumulated negative m. So the prefix at that point must be less than the prefix at L minus m. Why are these two removed? Well, these 2 points are the points I removed. These two minimums. Well, technically there's a third minimum here as well, which so I remove all these lines. So I removed this minimum, this minimum, and this minimum because they're not below the threshold where you have to borrow money. So there's two things you have to consider. Are they below the threshold, and are they below the smallest element that came in a range prior? So that's why I removed this element and these elements. Then why don't you just store the ones below the threshold? Because depending on my query, the threshold might be different. L can change. So I have to store all of them, and then I can just binary search to get rid of them when I query. So now to building this segment tree, and I'm not going to cover finding the minimum prefix because that's just building a minimum range tree. So I'll just go straight to building these minimum change arrays for each node in the segment tree. In actual fact, you can basically just do it, and it works in n-log-n, worst case. And the reason for this is, well, I'll start with the leaf nodes. So I'll draw a segment tree, or attempt to draw one. So in these leaf nodes of the array, they correspond to a single element. So what's the minimum change array of a single element? Well, it's just that element, right? So all of these, you have to do O1 work. Now, what about these nodes above? I'm merging these two arrays of size 1, and in the worst case, I have a strictly decreasing sequence, in which case I won't have to remove any elements when I merge them. So this isn't merging with the query, this is actually merging them. So basically, if I was to merge these two, I would actually physically remove these and then just plop that on. And then I would get an array like that. Yeah, so the leaf nodes have one element, and in the worst case, no element is removed when we merge, so therefore we can have two elements in the layer above. And continuing this logic, we'll have double that in the next layer, and then double that in the next layer. So if I make a table where I'll have S for the size of a single node, and then N, the number of nodes. On the bottom layer, I'll have, actually now I'll rename this. Make it S for the size of each node, and then C for the count of nodes in that layer. So on the bottom layer, we have N nodes of size 1. In the next layer, we have N over 2 nodes of size 2. And then the next layer, we have n over 4 nodes of size 4. And so these two just cancel out, because we've got n on 2 nodes of size 2, so therefore we have n nodes in total. We have n nodes of size 1, therefore we have, not n nodes, n elements if we counted the number of elements in every minimum change array. And so it's just n times the number of layers in our segment tree, and the segment tree has log n layers, so therefore it's n log n. Yeah, this is worst case. I'll explain average case later, because that's actually very interesting. Maybe I'll go on to the average case now. So this is the worst case complexity, and we would see something like this if we had an array that was a prefix array that was strictly decreasing, which we would get from an event array which is all negatives. And it's pretty clear why this would cause the worst case, because when you merge two halves, well, all of the elements on the right are always greater than the elements on the left. So you never remove elements when you merge, which causes worst case. What about average case? This is an array of size 8, but what would be the size of the minimum change array? Well, obviously the first element is in it, because the minimum, if I'm iterating over here, maintaining the minimum at the first element is obviously just that element. And now this element is greater than this element, so obviously it's not a new minimum, so it's not in the minimum array. Now this element is smaller, it gets added to the minimum change array, and now all of these elements are greater, and therefore won't get added to the minimum change array. So we have an array of size 8, but our minimum change array is only size 2, which is nowhere near what we would expect from ON. But what's more common? Cases like this, or the worst cases where we have this n log n behavior? I'm not going to formally prove this, but it turns out that on average, if I have an array of size s, the size of the minimum change array will be on the order of log s. I can give you an intuition for this. The minimum element of this array is obviously going to be in the minimum change array, right? And where will this minimum element occur on average? The minimum element is, on average, in the middle, right? And after we've come across this minimum element, no element to the right of it can be less than the minimum element. So, just by considering the minimum element, all of these are no longer candidates to be in the minimum change array. Now we can just repeat the same logic for what is the minimum element in this left side. It's probably going to be in the middle on average, and therefore we can ignore all of these. And so for each element you add in the minimum change array, on average, the number of elements which are candidates for the minimum change array halves. And that's where the log complexity falls out. Okay, so that means this s is not going to be doubling each time, because the size of the minimum change array is not equal to the size of the array it corresponds to on average. In fact, it corresponds to the log of it. So rather than doubling each time, it's going to increase by 1 each time, right? So if I continue on this on, although it doesn't work with this sec tree, I would have n on 8 of size 8 and n on 16 of size 16. But on average, it would actually be 1, 2, 3, 4, and 5. And so what's that do to the overall complexity? I'll write this out more formally. Basically, we've got the sum of I equals 1 to depth, let's just make it infinity, and because we want to know what this ends up being as n gets really large, of I on 2 to the I. What does this end up converging to? And it does converge. And it turns out it converges to 4. Okay, so let's expand this out for the first couple of terms. So we've got 1 on 1 plus 2 on 2 plus 3 on 4 plus 4 on 8, etc. Let's rewrite this as 1 on 1 plus, in brackets, 1 on 2 plus 1 on 2 plus, in brackets, 1 on 4 plus 1 on 4 plus 1 on 4. Now you'll see why I did this in a second. And let's just call this T1. Okay, so you all know the sequence 1 on 1 plus 1 on 2 plus 1 on 4, etc. And you're all convinced that equals 2? Let's call this T2. I can show you like a very, again, hand-wavy proof. Basically just, okay, let's make this a block of size 2. I add 1, so I cut this block in half. I add a half, I cut it in half. I add a quarter, I cut it in half. And I'm always cutting the difference between 2 in half. And as I go into infinity, eventually it just equals 2. So yeah, this infinite series equals 2. And with this, we're going to prove that this infinite series equals 4. Let's take out this infinite series from T1, because we've got a 1 on 1, we've got a 1 on 2, 1 on 4, so let's just see what happens if we take out T2. So T1 minus T2 equals, so we cancel out the 1 on 1, now we've got a 1 on 2, plus, we've taken out 1 1 on 4, so we've got 2 1 on 4s, and so on. So you'll have 3 1 on 8s, 4 1 on 16s, so on. And this looks very similar to T1. In fact, if I multiply this by 2, it equals T1, right? Because I got 1 half multiplied by 2 equals 1. I've got 2 quarters, multiply each by 2, and I get 2 halves. I've got, well, I have 3 eighths in this ellipses, and multiply them by 2, and I get 3 quarters. So 2 times T1 minus T2 equals T1, right? So therefore T1 minus 2, because T2, we know T2 equals 2. So T1 minus 2 times 2 equals T1. And if we rearrange this a little bit, we get T1 equals 4. And there you go. So the sum of the sequence converges to 4. So it has no term of n, it's just a constant. So we no longer have n times log n, we've got n times 4. So the average complexity of building this segment tree is actually ON, which is pretty cool. And this logic is actually the exact same that you would use to show that you can build a heap in ON, which I can go over after if everyone wants. Okay, so building this segment tree is n log n worst case and order n best case, or n average case. Now on to queries. So suppose we had worst case ranges and we've got log n of them. Well, binary searching on each minimum change array takes log n because they're order n in size, and so therefore each query takes log squared n, which is kind of hand-waving the fact that the ranges in the segment tree are of different sizes, but it does still work out as log n. And I can go over it more formally, but so log squared n as in order log n times log n. So it just means I'm doing log n work log n times. But we know that on average these minimum change arrays aren't order n, they're actually order log n. So rather than doing log n work log n times, we're doing log n log n times, which is a bit of a mouthful, but queries have a worst case of log n times log n equals, it's just the same thing as log squared n in worst case. In an average case, it's actually log n log log n. And that's basically it. That's the solution. And the final complexity is order. So it takes n log n to build, and for each query we are doing log squared n work. So we've got a worst case complexity of order n log n plus q log squared n. But our best case, or average case I should say, takes n to build, and for each query it takes log n log log n work. And this is not as good as Kwang's log n solution. However, in practice it actually outperformed it significantly, and that's just because it has a really good constant factor. In fact, I'm pretty sure on DMOD it's like 5th fastest. And there you go, that's Kwang's solution. And that's basically it. So let's move on to building a heap in order n. Okay, so this is a min heap. Okay, so you know that inserting an element is log n. So if I was to just insert elements one by one, then I would construct the heap in n log n. So if we want to construct this in order n, what we're going to do is just take our array and insert it randomly into our heap. Now this might not make any sense for now, but it will. So here, let's take this array. So let's say the 2 is here, and you've got this 3 is over here, 5 is here, 8 is here, then 4, got another 5 over here, 6. Okay, so that's the first step. We just randomly insert elements into a heap. And now what we want to do is heapify this, and we're going to do it layer by layer. So when I mean heapify, I mean, suppose I heapify some node, then I want this node and its entire subtree to obey the heap property. Now, for the bottom layer, that is pretty easy to do. With just one element, of course, it obeys the heap property. So immediately the bottom layer is done. Now let's move on to the second layer. So I'm going to heapify the elements in this layer, and what I want to do is swap the smallest element out of these two with this 5, because the 4 is less than 5. So if I want to obey the heap property, this 4 needs to go where this 5 is. Okay, and now I'll do the same with 8. So the 2 is the smallest one. I bring that up. And now you can all agree that 2 and 4 have been heapified, right? If I just look at this subtree on its own, yes, that could be a heap. If I look at this subtree on its own, yes, that could be a heap. Now, I have to heapify the final layer. And to do that, I'll take the minimum element of these two and move it up. Because 2 is smaller than 3, therefore if I want to keep the heap property, 2 should go in place of 3. And now 3 is smaller than 8 and 5, so it doesn't need to move any further. So we have just heapified this random sequence of elements. And this is actually order-n. And it's order-n for the same reason that, on average, building this segment tree is order-n. Now that might not be immediately obvious, but let's take a look. So in worst case, all these elements in the bottom layer, they never have to move to be heapified. In the second layer, they have to move at most 1. In the third layer, it could move twice, right? Or more formally, I have n on 2 elements which could move 0 times. I've got n on 4 elements which could move once. And I've got n on 8 elements that could move twice. And if I had a bigger segment tree, this could keep going. So I could have n on 16, 3. And this should look very similar to this. So n on 2, 2, n on 4, 3, n on 8. So this is offsetted, but it's the same thing. And for the same reasons that this is a constant, this too is a constant. And therefore, this procedure takes order n time. Well, I guess that's it then. Bye.